Okay, so now let's start with the examples. I have a bunch of examples to show you here. And please, while listening to this, so make sure you have your Laplace table to this. I mean, I can scroll back like this, but the thing is that it's going to be helpful for you if you have the table with you right now. I did mention to you before, every single time you study for Laplace transform, that table should always be your best friend, should always be with you. So either you can print and had a copy of that, or just snap a picture of that and make sure you had it in your phone. So when I show you this example, you should be referring to the table. Alright, so for this particular example, what we're going to do is we're going to use the Laplace table to find the Laplace inverse of this particular expressions right here. I'm going to have how many of them? So there's going to be 6 examples, which is going to be all different. Okay, so I'm going to start with the first one. So I'm going to find the Laplace inverse of 101 over s. Again, as I mentioned to you just now, every single time you want to Laplace transform, the denominator, the lower part of the fraction, is going to give you the idea. So what kind of function is this going to be converted to? And now I have s to the power of 1, and it could either only be constant or exponential. But it only becomes exponential when your s to the power of 1 is accompanied by plus or minus a constant, which is not the case for this one. So therefore, we would be referring to this one, for which we know that Laplace inverse of a over s is going to equal a. And what is going to be our a value for this case? My a value, that is going to equal 101. Okay, so that is why when I use the table, so Laplace inverse of 101 over s, so that is going to equal 100 of 1. So that is because of this theorem right here, the fact that if I were to Laplace inverse of a over s, so that is going to equal a. So that's my a value. So that is why it becomes 101. Okay, number 2. So I'm going to find the Laplace inverse of 2 over s plus 4. Again, here I come across s raised to the power of 1. But the difference is that now it is accompanied by a plus 4. So automatically we know that if you have a plus 4 or minus something, automatically that is going to be in terms of an exponential. Okay, let's have a look. What is the requirement to convert this to an exponential? Okay, in order to convert this to an exponential, so I need to have 1 at the top, and at the bottom it should be in terms of s minus a, or s plus a. So which is going to be s plus a for this case. Alright, so what we can do is, this 2 right here, we can actually move that to the front, because according to the table, we don't need it. So the linearity theorem, let me put over here, I put a star right there. Linearity theorem, it works for both Laplace and also Laplace transform. Sorry, Laplace and Laplace inverse, not Laplace transform. Okay, so it's going to work for both of them. So whenever I have a constant like this, a 2 right there, and I don't need it, I can simply pull that to the front. So therefore I can write that this is going to equal, so I'm going to pull the 2 to the front, 2. So Laplace inverse of 1 over s plus 4. So it now looks similar to what we wanted, because I need it to look in terms of this 1 over s plus a. And for this case, what is going to be my a value? So this is going to be my a value. My a value is going to equal 4. So therefore automatically this is going to be converted to 2. I just copy it down. So this function over here, according to the table, so that will be converted to exponential to the power of negative 40. Remember I told you, if this is a plus, the power of the exponential is going to be negative. They're going to be the opposite. So the thing about the table is that you have to make it exactly the same, or in Malay it's called sebiji sama, then only you can Laplace inverse. Like, why do I say sebiji sama, for example? So let's say for sine, you need a at the top. You can only convert this when at the top is actually a, and it is exactly as what you have in the table. If it's not the same, automatically you cannot convert. You have to change your function. So I will show that in the later examples. So that is why here for this case, so that is why I changed this to, instead of 2, so I changed that to 1 instead. Okay, let's proceed to the third example. So third example, I have Laplace inverse of 3s over s squared plus 4, and we have seen that before. If this is to the power of 2 being accompanied by a constant at the back, so if it's a plus, So it could be either two of this. It could be either sine or cos, depending on what goes on top. If I only have constant, so it's going to be sine. But if I have s at the top, automatically that is going to be cos. But for this case, I actually have both. But bear in mind, so the fact that, remember linearity theorem, the 3, I can actually pull that up to the front. But I cannot do the same to the s. So that is why when you have a constant and s at the top, the priority will be on the variable, which is going to be s. Automatically, this will be converted to a cos function. And according to the cos function, what do we need according to the table? So I need again the value of a, and at the bottom of here, this is going to be a square. So let me change it according to the table. So this is going to be a 3. I'm going to pull that out. So Laplace inverse of s over, now I'm going to write it in terms of s squared plus 2 square, okay? Because here for this is my a square. So it's going to be much easier. Right away I can tell that here my a value that is going to equal 2. Okay, so now this is exactly the form as you have in the table. I have s at the top, s squared plus a square at the bottom. So automatically this can actually be converted straight away to 3. So this is going to be cos of a, which is going to equal 2. So I'm going to have 3 cos of 2t. So that is going to be for the third example. Remember, so the priority when you have a constant and s, the priority will go to the variable because the constant can be pulled over to the front. Okay, the fourth one, I have a Laplace inverse of 4 over s squared plus 2. Okay, now I'm going to make it a little bit more complicated now that we have seen so much. Alright, so what I am going to do next is, if you have a look at the function, so again, we have s to the power of 2, right away we can tell, and because of the plus right there as well. So this is going to be converted to a sine, because at the top is going to be a 4. It's a constant. And according to the table, if I have a Laplace inverse of a over s squared plus a square, so that will be converted to sine of at. Remember, at the bottom right here, this is going to be your a square. And for this case, what happened is that my a square is going to be given by 2. And that tells us that a, the value is going to equal square root of 2. So do not get intimidated by that. That is just a number. So a square is equal to 2. A is going to equal square root of 2. So that could happen as well. Okay, however, another thing is that, so if I wanted to use this particular formula, so I have to make sure that at the top is going to be a as well. Then only it becomes sine of at. But we have a major problem right here. I don't have a square root 2 at the top. In fact, I have a 4 at the top. So now I'm going to start to make things more complicated. I'm going to show you how to manipulate your function in order to make it exactly the same as what you have in the table. Okay, now let's start. Listen very carefully. And listen to this over and over again if you have to. Okay, so now I'm going to rewrite this. I'm going to rewrite this as a Laplace inverse of 4 over s squared plus square root 2 square. Square root 2 square is simply going to equal 2. Okay, however, the problem is that I have to change at the top. So this cannot remain as being 4. It has to be changed to a square root of 2 in order for me to be able to use this formula right here. So I'm going to do this. I'm going to use algebraic manipulation. I'm going to change the form. Okay, in mathematics, it is always possible to change the form. For example, so instead of having some like 1 multiplied by 6, this is actually equivalent, the same as writing this as 2 multiplied by 3. So as long as the value remains, this is going to equal 6. This is going to equal 6 as well. So these two are basically the same, only the form is different. And that is totally possible. So you can change any function any way you like as long as you retain the value. So that will be the main point. The value has to still be the same even after you change them. So let me clean this. It looks too messy or else. Okay, so now I'm going to start doing something to this function. What I'm going to do is I'm going to start multiplying this by something. I'm going to start by multiplying this by 1 because I know that 4 multiplied by 1, so that is still going to be 1. Right? So that is the first step. So the next step I'm going to do is I'm going to write this as a Laplace inverse of 4 over s squared plus square root 2 square. But instead of 1 from before, this is my 1, I'm going to change the 1. I don't want to have 1. I want it to be in terms of square root 2. And we know a fact that is for sure. So the fact that 1 is actually equal square root 2 over square root 2. So that is what I'm going to do. I'm going to create a square root 2. So I'm going to create that from 1. I'm going to write that 4 multiplied by square root 2 over square root 2. So that is still going to be 1. I do not change the value. So it is still going to be the same. Alright, so let me cheat that a little bit more. So instead of leaving this in this form, right? So remember, I needed an a. I don't need anything else. So I'm going to separate them. I'm going to write it in different form. I'm going to write this as a Laplace inverse of 4 multiplied by 1 over square root 2. So multiplied by square root of 2, and that is going to be over s squared plus square root 2 square. So let me add another the page after this. Okay, so that is how it's going to look like. All right. So I only needed this one. So this is the only thing that I need that should retain in there. And this is simply a constant that I don't need. So what I'm going to do is I'm going to apply linearity theorem and bring them out. So only retain whatever that you need. Okay, so when I pull out the 4 multiplied by 1 over square root 2, so this is going to be 4 over square root of 2. And in here, I'm going to have a Laplace inverse of square root 2 over s squared plus square root 2 square. Right? So this is what we wanted. We have achieved what we wanted. So I have a at the bottom, a squared at the bottom. And this is my a value. They are now the same. They are exactly in this form right here. Then only I can convert my function to sine of at. So therefore, for this case, so this is now going to be equivalent to 4 over square root 2. So this is going to be sine of square root 2t. Yeah, I know this can be quite confusing to you, but take your time and try to understand them. Remember, you can only use the table when they are convert that to the function when they are exactly the same. If they are not exactly the same, then that is not possible. So therefore, you have to change your function, but it has to be mathematically correct. The value has to retain, then only you can use the Laplace inverse table. Right? Okay, pause for a bit if that can confuse you, and have a look at this until you really understand what's going on. But now I'm going to start showing you a next example, but it's actually going to be a recap. It's going to be a repetition of what I've seen before. I have discussed before in example number 4, but it's going to be in different form, like more example for you. Okay, so now I'm going to have a Laplace inverse of 2s minus 7 over s squared plus 16. So now if you have a look at this, what comes to your mind? I have x squared plus 16. So with this going to be, so let's put a minus instead of here. We've seen enough of cos and sine. So let's make it in terms of, that's alright, we have cos and sine at the bottom. So let's leave it that way. Okay, so I have 2s minus 7 over s squared plus 16. If I have a look at the top, I have a combination of constant and s at the top, numerator. And I also have 7 by itself right there. So is it going to be sine or cos actually? But if you have a look at the function very carefully, this is going to be a combination of both cos and also sine. Why? Because of the minus right here. Remember the linearity theorem? So this function can actually be separated into two functions, which is going to be Laplace inverse of 2s over s squared plus 16. So let me put the s4 square, because we know that at the bottom is going to be a square. So minus a Laplace inverse of 7 over s squared plus 4 square. Right, so that is going to be the combination of my function. Right, so I separate them into two. Like here, because of this s right here, I know that this side, this is going to be cos, and because of the 7 by itself right there, constant by itself, so this is going to be a sine, and both of the a values going to be the same. It's going to be a value of 4. However, that will be a little bit of complication here. Okay, for this one, I can tell right away. So I can put the 2 to the front, and this is going to be 2 Laplace inverse of s over s squared plus 4 squared. But for this one, this is going to retain as a Laplace inverse of 7 over s squared plus 4 squared. And here I'm not going to have any problem. I already have s at the top. As I mentioned just now, we know that this is going to be sine, and my a value is going to equal 4. And we can convert this to right away to 2 cos of 4t. But it's not going to be possible for this one, because here, remember, our value of a is going to equal 4. But I don't have a at the top, but instead I have a value of 7 when I should have 4 at the top. So that is why I'm going to use the same trick that I used just now. Okay, let's do the calculation somewhere down here. So now I need to find what is going to be the Laplace inverse of 7 over s squared plus 4 squared again. So I have a problem right here because of the 4. I need 4 at the top, but instead I have a 7. So that shouldn't be the case. So therefore, I'm going to manipulate this function according to what I wanted. So here, I'm going to change this. I'm going to write this as a Laplace inverse of 7 over s squared plus 4 squared. And I'm going to write here the fact that the 7, I'm going to multiply that by 1. Because 7 multiplied by 1, that is still going to be 7. They're still going to be the same. But remember, I don't want a 1, but in fact, I wanted a 4. So I'm going to make it into my 4. So I'm going to write this as a Laplace inverse of 7 multiplied by 4 over 4, which is what I wanted. And it's going to be over s squared plus 4 squared. Okay, because 4 over 4, that is still going to be 1. This is still 1. Right? And then the next thing what I'm going to do is I'm going to remove whatever that we don't want in there. So the only constant that we need is going to be the 4 right there. We don't need anything else. So therefore, anything else is referring to the 7 and 1 over 4 right there. So I'm going to pull them both out. So that is going to be 7 over 4 of a Laplace inverse of 4 over s squared plus 4 squared. So now the good news is that we already have the form that we wanted. And this is 4 at the top, 4 at the bottom. So right away I know that this can be converted right away. And this is simply going to equal 7 over 4. I'm going to have sine of 4t. So I can put right here. So the fact that here I'm going to have 2 cos of 4t minus 7 over 4 sine of 4t. Right? So this is going to be the final outcome. Right? So this might be confusing to you right now, but as time goes by, if you have done enough example on this, so this will come naturally to you. Remember, I mentioned just now, you can always modify a function, but just make sure that the value retains. Okay, next, number 6. So I'm going to find the Laplace inverse of 3s plus 2 over 2s squared minus 8. If you notice, this is actually very similar to the previous one. The only difference is that I have a minus previously, but there's a plus. But there's no problem with that. I can still apply the linearity theorem. However, the thing is, there will be one major difference right here. Okay, I forgot to mention to you in the table right here. So the similarity between all the terms right here is that, so let me clean that a little bit so that you can see that clearly instead of having all this mess right there. Okay, the fact that all the coefficient of s is given by a value of 1. This is 1s to the power 1, 1s, 1s, 1, 1, 1. Everywhere in the table, the coefficient is given by a value of 1. Okay, what if you come across something like this, that the coefficient is given by a value of 2? So the first thing that you have to do is you have to make sure that the coefficient is given by a value of 1, and that can simply be done by factoring out the 2. So I'm going to end up with, so I'm going to have a Laplace inverse of 3s plus 2, and that is going to be over 2 multiplied by s squared minus 4. And make it a habit, like after you do the factorization, please multiply them and make sure that it become the same function as previously. When I expand this, automatically I will get 2s squared minus 8. If you don't get the same function, then your factorization is wrong. Alright, so now that I am done with those, I'm going to pull out whatever that I know I didn't need, and I'm going to start apply the linearity theorem. So what do I mean by whatever that I don't need? I'm referring to the constant right here. I don't need to be there. I'm going to pull that out. So I'm going to write that this is going to equal, and put right here in case we don't have enough space. And this is going to be 1 over 2. Then I'm going to start separating. So my first Laplace inverse is going to be for 3s over s squared minus 2 squared, because I know I need a value of a, and now my a value is going to equal 2. And the other one is going to be plus a Laplace inverse of 2 over s squared minus 2 squared. And previously we always have the case of plus, and now we come across the case of minus, and we know the only difference is that if that is a plus, that is going to be in terms of sin and cos. When that is a minus, it's going to be either sin and cos, but the idea is pretty much the same. Okay, here what happened is that so I missed out a bracket. I have another bracket right here. Okay, so let me put the bracket in a different color so we don't miss it out. The fact that the whole thing is going to be multiplied by a half. Okay, so that is how my function looks like, and this is going to be a half. Okay, and remember linearity theorem, I can pull out the 3, so this is simply going to end up with a 3 cos of 2t, and my bracket of course, and plus, and here I don't have to change anything anymore because I have a at the top, so this is my a square. They are already in sync, right? So I don't have to do any more algebraic manipulation, so that way I can change that. This is going to equal sin of 2t, so that is going to be the outcome, right? So that's how my function looks like. I'm going to end up with a half of 3 cos 2t plus sin of 2t. Remember, so if the coefficient is not equal 1, factorize, get rid of the constant, and then only start using the table. I know this is going to be new to you, but it's going to be similar idea to Laplace transform. As long as you do enough exercise, so you should be able to do fine. But the rule is that enough exercise. So try to do the exercise that you have in the book, and of course the extra exercise provided by your lecturers as well. So that should be, as long as you've done all those, I'm sure it'll be fine.